Welcome to the last Math Plus Friday in this wonderful summer semester. We ordered perfect weather and it was delivered. Let me tell you one thing that impressed me last week. So on Wednesday, I had interviews with our phase 1 students. So we have this event, Meet the Chair, where we have a series of interviews, and I'd like to let you all know that that was a very impressive thing for me. So seeing all these students really live in your office, that was a very rich experience. Somehow we talk a lot about diversity, and we have all these numbers. There are so and so many students, but then talking to them in person was wonderful. So we have wonderful people, I must say. And I'd like to report on one aspect that I learned there during those interviews. So I asked this open question: are there any, do you have feedback, positive feedback, negative feedback? And it was overwhelming, really overwhelming, that essentially everybody said, well, the office is doing great work. They are a fantastic support. And I think we should maybe use this opportunity to acknowledge that as well. Then you probably all know the overview of today. So there will be the math talk, and then there will be a dissertation award, and then there will be a party. So you all have to stay. But for now, I hand over to Rupert in order to introduce the speaker. Please.
Hello, I'm Rupert Klein, and I'm very glad to welcome Christian Kuehn for today's lecture. Christian is, let me just count a little bit of out of his CV. He studied mathematics in Bremen at Jacobs University, and then he actually went to explore the world. He went to Cambridge, where he got his master in applied mathematics, and he went to Cornell University to receive a PhD. He then went as a postdoc to Dresden, to the Institute for Physics of Complex Systems. And then he was a postdoc in Vienna at Technical University in the Analysis and Scientific Computing Institute. And then he received the Lichtenberg Professorship funded by Volkswagen Foundation. And that allowed him to move to Munich to get a chair there, which he still holds. The funding got prolonged, and I think in Munich, people are very happy to have him there. Let me report a little on his work, because that is something that we really very well covers Math Plus aspects, but also aspects of our CRC 1114 scaling cascades in complex systems. Christian is an expert in multiscale dynamics, from differential equations through networks, from stochastic, deterministic to stochastic, from formal analysis to rigorous. He covers the whole ground, and actually he wrote an encyclopedia of multiscale methodologies in multi-time systems, which I very much recommend. He is very well known for that work, and he's deriving his wonderful mathematics from these foundations, and I'm sure we will hear a lot of this. He also received, for example, the Richard von Mises Prize of the Society for Applied Mathematics and Mechanics, and he was a Oberwolfach Leibniz Fellow for a while. The list of awards and grants that he received is many pages long, and I stop here and rather look forward to a very interesting talk with lots of mathematics and multi-scale in it.
Yeah, thanks very much. I hope you can hear me well. Is that okay in terms of sound? This micro is slightly strange, so Has to be very close, apparently. So yeah, thanks for the very kind introduction, Rupert. So that it's a pleasure to be here. I've been to FU many times and also to Berlin many times before. And yeah, today I have sort of a difficult task, I think, because I'm sort of the problem in a way between you and the party. So that makes it slightly tricky for me to convince you that you should listen. But okay, I will give it a go. Okay, so what's the plan for today? Let's see. Okay, so what I'm trying to cover is basically a little bit of background first because I think it's a diverse audience. I will try to figure out to bring you all along, at least for the sort of first 35 minutes or 40 minutes of the talk. Give you a bit of background on what fast, slow differential equations are and where they came from, and a concrete example that's from a textbook, basically. And then I will tell you what are the general techniques in the field so that you at least learn what techniques are we using. And it's actually very connected to many other areas of mathematics, which I think is great. I enjoy that a lot. As you heard from Rupert, I try to sort of connect different branches of math. And then I will go on in the sort of last 15, 20 minutes. I will try to explain a few new results that we have achieved. And my list of collaborators is there. And one name you might recognize, Maxi Engel, who's in Berlin. Over there. So that's great to see people who I've worked with. And that's a sort of long-term story where we are trying to figure out how to somehow lift multi-scale methods from finite dimensional differential equations to infinite dimensional differential equations. And that's generally hard. And I will explain why. Yeah. Okay. So where do small parameters and multi-scale methods come from? So this is a quite famous cover of Henri Poincaré's book Mécanique Céleste, and the guy next to the book cover is Poincaré, a picture of Poincaré, I think taken in the 1880s sometime. And he discovered that it's useful mathematically to sometimes view a problem as perturbative. You know, you have maybe two bodies that are revolving and then maybe a little body that's, you know, maybe a moon or whatever that you're trying to understand in a dynamical system. And there's a sort of perturbative idea that it's helpful to think in terms of scales. So there's sort of a length scale and a time scale. And you should try to exploit this structure, because if you don't, then if you have a general sort of nonlinear system where you don't exploit these lengths and timescales, it's very difficult to analyze. And Poincaré in this very nice monograph figured out that for celestial mechanics, this is a very useful technique. Yeah. So he is a giant of the field, but there are more giants of the field. Always have to click twice here somehow. I don't know. Yeah, so that's the second person I want to briefly introduce. This is from the ICM proceedings, I think from 1904, if that's right, if I recall that correctly. Yes. So this is Ludwig Prandtl, who discovered this not on a scale of planets, but he looked at small parameters and asymptotics and multiscale problems in fluids. And in particular, he looked at this in the context of the classical Navier-Stokes equations already. And there's one thing that you can read, so it's quite interesting. Das zwei- und dreidimensionale Problem mit Berücksichtigung von Reibung und Trägheit hart noch der Lösung. Der Grund hierfür liegt wohl in den unangenehmen Eigenschaften der Differentialgleichung, which I think is quite a nice thing. So he says, to translate, so Navier-Stokes in 2 and 3D with all sorts of stuff in it is really difficult, and you can't really treat that because it is actually one of the hardest multiscale problems we have. And the problem is still there and it's not solved. And he says, well, the reason is probably the unpleasant properties of the differential equation. Yeah. So, and indeed, it is an unpleasant equation to look at. So what we will do in this talk, we will not aim as high as something like Navier-Stokes, which is effectively one of the millennium problems and one of the hardest problems we have, but we will try to maybe slowly develop some methods that at least try to understand how multiscale structures help us to analyze differential equations that are PDEs and not only ODEs, so partial instead of ordinary. Okay, somehow this Plipper thing is strange. So here's the textbook example. So this is the Van der Pol oscillator. So this is just a two-dimensional planar ordinary differential equation with two variables. So u, that is the fast variable, because there's actually an epsilon that's in front of the slow variable v, which means that roughly speaking, you anticipate that u evolves quickly because v evolves slowly in comparison to that, because it's pre-multiplied by a small parameter. Right? That's sort of intuitive. It's a normal vector field, like you know from your analysis 1 or 2 or 3 course or whatever. Yeah, but if you put in a small parameter, then there's a scale separation, so u will evolve very quickly generically. And then V you anticipate to evolve slowly, but there's some sort of interplay between these variables. And let me see, somehow I click these, it doesn't really move forward. Do I have to point somewhere? Yes, maybe I need to be closer to point somewhere here so that it picks up the signal. So here's just a starting point. So first you observe that Q00, so U is equal to 0, V is equal to 0 is an equilibrium point or a steady state of this system. So it doesn't move at all. But if you take 4 initial conditions sort of next to it, you see that seemingly if you integrate that forward is an unstable steady state. And these initial conditions really sort of seem to fly off almost horizontally when you let the differential equation run. That basically means that only sort of U is active and the slow variable V doesn't really move very much, or at least it only moves very little. So that's why these arrows are basically horizontal. Yeah? So mathematically, this hopefully gives you a structure how you can analyze what the solution structure of this differential equation is. Yeah? So maybe do that. Yes, this is the trick. Okay, so I should stand here, I guess, but then the camera doesn't pick me up. So it's a really tricky thing. Fair enough. So now, if you think mathematically, the first thing you would do is you would try to say, okay, epsilon is assumed to be small. But if it's assumed to be small, then why not be mathematical and take the limit epsilon tending to 0? Well, this is quite natural, right? So you take your differential equation, you send epsilon to 0, and what you get is actually just a parameterized differential equation for every value of u, because u is constant, u prime in time is 0. For every fixed value of u, you have a one-dimensional differential equation. And these one-dimensional differential equations you can analyze quite easily, and you see they have either 1 or 2 or 3 equilibrium points. And I've drawn in the arrows completely horizontally in this sort of singular limit phase portrait that shows you that, for example, up here, so up here you actually have a stable guy, then you have another stable guy here, an unstable guy in the middle, and then another stable guy, and then you can draw in the flow of this singular limit system for different values of u quite easily. For different values of v, yes, for different values of v, yes. But v is fixed, and for different values of v, we have, as it says, different values of v, we have the so-called fast subsystem that's horizontal, and on these horizontal lines, you have a movement that you can calculate effectively, or at least say qualitatively where the trajectories are going. Okay, so that helps us. Oops. But now there's actually a second limit system, which happens if you take your original system, you scale time, and if you do that, the epsilon moves from actually it was over here, and it moves over here upon a time rescaling. So this time rescaling you can do for any epsilon positive, and then you just move that epsilon in the differential equation to a different place, and then you can again take the limit epsilon tending to 0. It's also allowed. But you then get a different differential equation, namely a so-called differential algebraic equation. I guess Berlin has been a sort of, I don't know, a center for differential algebraic equation for many decades, I guess. So this differential algebraic equation, there's an algebraic constraint, which is this cubic curve of this van der Pol oscillator, which is the sort of first equation, the only nonlinearity that you have. And then on this cubic curve, there's slow dynamics in V, and you can again calculate what that slow dynamics in V is. There's one equilibrium point here in the middle, and then there's 2 sort of special points where you see that the flow is pointing inwards and you don't quite know what to do at that. But otherwise everywhere else except for these 2 special points, the fold points, which are the local max and the local min of this cubic curve, you know very well what's going on. So you can calculate very precisely what the flow is doing in this slow singular limit, because you are now on the time scale that's slow in comparison to the previous time scale, because you rescaled your original time t by epsilon. So here you rescaled it by epsilon. So this means this is a slower scale in comparison to this faster scale t, because you multiplied it by epsilon, right? Very reasonable so far. So, but now you can combine these 2 subsystems, and you can think, well, if I start with a generic initial condition, what should happen is, if I start somewhere here, for example, I should first go over here horizontally with the fast system, because that's the fastest scale. Once I have reached this so-called critical manifold, this sort of gray curve, I actually can move on this with the slow subsystem slowly. At this fold point, I get pushed by the slow flow and slow subsystem into this point. And then I again should switch to the fast subsystem. I make a fast jump. Then I get sort of land over here at this so-called drop point. I move down, and then I move over, and I have this limit cycle behavior. which is rather neat. So this means if you combine the fast and the slow subsystem, you can actually generate a very nice geometric description of a periodic solution for this classical van der Pol ordinary differential equation in the plane. I guess many have seen that maybe in a basic differential equations course or so, because the van der Pol oscillator at least is something that's often treated in these basic courses, right? Is that right? Still hopefully done somewhere. Yeah, okay, so this is nice because it gives you somehow a geometric description of a multiscale system by decomposing it into its different scales, namely into the fast scale, which are these horizontal jumps, and to the slow scale, which is this movement on this critical manifold, this cubic curve for the van der Pol. Yeah? And if you then integrate forward an arbitrary initial condition for epsilon small but positive, but not for epsilon 0, because you constructed this sort of singular orbit or this candidate orbit for epsilon 0, but if you then integrate forward an arbitrary initial condition like this, then you see indeed there is a limit cycle emerging or a periodic orbit emerging. So this is the orbit that you get from, say, numerical integration or asymptotics. And that orbit matches quite well the dark black orbit that we have derived in these two singular limits that we have basically constructed by combining the two different scales that are in the problem. Yes. And of course, there's a deviation, and mathematically, in physics, you would probably say, well, there's a tiny deviation. And if epsilon tends to 0, this deviation goes to 0, and it does. But in math, you might want to measure it, and even measuring this deviation turns out to be quite difficult. So there have people written just sort of 250 pages of books just about trying to figure out this little deviation here. So it's actually by no means easy to figure out what that deviation is. Yeah, so it looks innocent, but it's surprisingly non-innocent. Yeah, despite the fact that the picture is intuitive for everybody. Yeah. Okay. So these are called relaxation oscillations, I should say. Yeah, because it's relaxing and then oscillating again, relaxing and oscillating and so on. Huh? Okay, very good. So, but then mathematically, you should think maybe we can generalize this structure to arbitrary finite dimensional systems quite easily. We had basically one fast variable u and one slow variable v. And then the idea would be, well, why not write this same structure that we have written up before in abstract form for m plus n dimensions? So you can take m fast variables and n slow variables, and you just have a coupled set of differential equations that's m plus n dimensional with a small parameter. Sometimes you can also do this if the small epsilon is not visible. That's so-called non-standard theory. But today I will do standard theory, which means that the small parameter is visible. If it's not directly visible, all of the stuff I'm saying here still applies. Okay, it's called non-standard fast-slow analysis. Yeah, not non-standard in the sense of non-standard analysis, but in the sense of that you don't see the epsilon explicitly. So here you see it explicitly, and we will sort of just work with this explicit epsilon on this u scale compared to the v scale. And then you can do the same tricks that we did for van der Pol. You can rescale. Yeah. Then you get another system where the epsilon has moved from over here to over here because you rescaled t to s to the slow time scale. And you can take these two limits. Yeah? You can take the limit, which is the fast subsystem on the fast scale t, which gives you a parametrized set of differential equations. And you can take the slow scale limit, which gives you a differential algebraic equation called the slow subsystem limit. And you see here more clearly maybe the point why this area is difficult. It's a singular perturbation problem in the very classical definition sense of singular, because the limit problems that you obtain in different scales are actually even non-equivalent structural systems. One is a parametrized set, and the other one is just a constraint system on which you evolve, which means that somehow the mathematical structures have diverged by taking the limit epsilon to 0. Yes, and that's what generally is defined to be a singular limit problem. Yeah? In other problems, it's regular. You basically would get, for example, two types of differential equation of the same form. Here it's singular because you actually get two different types of differential equation in the limit. Huh? I need a little bit of terminology, a few definitions that I will use throughout the talk. So that's why I introduced them here. So the first thing is, of course, this set f is equal to 0. It needs a special name, because you see on the system on the left, this is basically the equilibrium points. F is equal to 0 gives you the equilibrium points or steady states of the fast subsystem. If you're on it, you don't move. And on the right side, it gives you the constraint, meaning if you're on this constraint, then that's where the slow motion is taking place. So obviously this should get a name, and this is called the critical manifold or critical set. Yeah, it doesn't have to be a manifold, but classically people call it a manifold. Yeah. Generally, you should probably say a critical set or a critical variety if you like. Yeah, and this is the main definition of regularity of this object. It's called normally hyperbolic if you linearize with respect to the fast variable. So you take your f, you differentiate, form the total differential, you get a matrix that's m times m, you calculate its spectrum, and if there's no spectrum on the imaginary axis, then we call this normally hyperbolic. Maybe let's go back to the van der Pol. Oh, I should go back. Is that possible? Yes, so here, if you look at the van der Pol, if you would do this, then you see quite easily, if you differentiate in the fast variable u, you see there are 2 points where you're not normally hyperbolic, which is the local max and the local min of this. Because if you differentiate, you get u squared minus 1, you plug it in, then you get plus minus 1, and then you see only the local max and the local min you are not normally hyperbolic, which are these 2 fold points. And at all the other points, the spectrum is indeed normally hyperbolic because you either get one eigenvalue which is positive or negative, because it's a 1 times 1 matrix in this example. Yes? Hope that's simple enough. I mean, I couldn't boil it down to 0 times 0, obviously. Yeah. So fair enough. And it's, of course, somehow called attracting if all the real parts of the eigenvalues of this linearization are on the left-hand side of the complex plane. And it's called repelling if all the eigenvalues are on the right-hand side, because if you know from linear systems of ODEs, if you solve a linear system of ODEs, then you know, okay, if all the real parts are negative, then it's contracting, so attracting. So this piece of this critical manifold is then attracting in the fast direction, and if it's not, it's repelling. And, well, it's saddle type, it would be if there are some negative and some positive in terms of real part. Okay, so this is quite natural as a definition. And there's a key theorem that I will state in some detail later on, but for now, you just should get the gist of the theorem. The gist of the theorem is that if you're normally hyperbolic, if this condition is valid, then in these parts of your phase space, there's a nice perturbation theorem that somehow says that you can just take your singular limit system epsilon equal to 0 near this critical manifold. If you're normally hyperbolic at such a point, you're allowed to perturb your system, and all your conclusions that you obtain from the limit, so from the singular limit epsilon equal to 0, by decomposing it into smaller dimensional subsystems, are sort of still valid when you turn on the epsilon and the epsilon is positive. Okay? So it's a good perturbation theorem. So roughly speaking, yeah, so there's a nice perturbation. Yeah, that's what I want to say. Yeah? And I will state the theorem in more detail later on, but be mindful that this is sort of a key regularity assumption in the subject called normal hyperbolicity. You could also say, if you're an algebraist, the linearization of the matrix is a hyperbolic matrix, if you wish. Yeah, if that's easier for you. Yeah, it's fine. Okay, so this is the abstract theory. And let me tell you a few things that people have developed from a top-down view as techniques to analyze these systems. Suppose there is a given structure of a multiscale differential equation. What are the techniques that people have used? And there's sort of a trichotomy in some sense. There's some streams of research. Some streams are sort of doing asymptotic research, which is sort of classical applied math, where you put in series expansions and you try to figure out how to match all these series expansions in the small parameter epsilon to figure out what the solutions are. Maybe people have seen this in some form or in some fluids course or whatever. Yeah, you see this quite often. So this is asymptotic analysis. Then there's a second stream that does sort of more geometric analysis and techniques that are sort of geared at, can we prove with the most elegant sort of geometric functional analytic setup a theorem circumventing this chunking of expansions as much as we can. Okay, this is sort of the second bullet point that I put here. And then there's the third bullet point that people have done algorithmic research, in the sense that they have looked at, can you find an algorithm to compute, for example, certain points on this critical set? Can I compute the perturbation, this perturbation from Fenichel and so on? Are there techniques to actually get these critical manifolds and their perturbations, so-called slow manifolds, upon computation? Yeah. So in the computational numeric, people have found fancy abbreviations for the methods. They're really good at this. So for the normally hyperbolic case, when you have this regularity assumption, classical regular asymptotic expansions work. And this is roughly the case of the van der Pol oscillator in the beginning, when you are away from these two fold points, away from the local max and away from the local min, then actually you can apply this theory and standard asymptotic expansions work. Yeah? Analytically, there's this abstract Fenichel theorem that originally in the attracting case was proven by Tikhonov in the 50s already, and then was refined and refined and refined, and then eventually Fenichel proved the most general thing in 1979. And then there's this algorithmic stuff, for example, the invariant low-dimensional manifold method and the computational singular perturbation method and the zero derivative principle and all sorts of principles that computationally how you can treat these systems, okay? And the same is true also for transitions between fast and slow motion. So for these transitions between certain multiscale areas, there's again asymptotic techniques where you now have to do more, meaning you have to match the fast motion with the slow motion in a suitable sense, like these sort of corners that you saw in the relaxation oscillator of the van der Pol oscillator. These are examples where you have to do matching. So you have to take one expansion and another expansion, compare coefficients and hope it works, yes? And mostly it will, but you have to do something, yes? It's very tricky to actually get that going. In the analysis, I won't talk about this today. There's a technique called the exchange lemma. So if you're in dynamical systems, that's sort of an upgraded version of the lambda lemma. Yeah, if you're a dynamicist, then you know what that is. And I won't talk about it today, but there's a geometric technique for this matching. And then there are also algorithms, and in general, many of these algorithms for transitions between sort of multi-scale problems are very well treated by boundary value solvers, interestingly enough. Yeah? Okay, and then there's this problem with the fold points, which is this local max and the local min in my standard example of the van der Pol oscillator. And there you have to be really sort of clever. You have to do really clever matching. Couple hundred pages of matching, in fact, until you get the right expansion. Or you do a technique that I will introduce in the following, which is called the blow-up method. I don't know if there are people from algebraic geometry here or so. This is the same method as you use in algebraic geometry. So you take singular points and you put in P1s or Pn's, and then suddenly they become non-singular. Yeah, so like Hironaka's theorem, basically. So this is just a differential version of Hironaka's theorem where you can desingularize certain points. I will talk about this a little bit. And then for algorithms, if you want to detect these points, there's lots of stuff on bifurcation detection where you figure out that these points, for example, these fold points are bifurcation points of the fast subsystem, and you can use all sorts of bifurcation detection algorithms to find them and compute with them. So this is this trichotomy in the field of multiple timescale techniques. And the red part that I've highlighted here is what we now know under the name of GSPT, which is geometric singular perturbation theory. So it's the idea of I want as much geometry in my problem as possible, and I will take this viewpoint of geometric singular perturbation theory for today's talk. But I just wanted to point out there's lots of other stuff. Yeah, so that's very important. Okay, let's go on a little bit. Yeah, okay. So there's used in many, many applications. Yeah, climate, neuroscience, epidemiology. There's hundreds of applications of multiscale analysis. I've only put 3 where I've worked on a lot and which are sort of maybe my personal favorites, but that doesn't mean, I mean, there's neural networks are of course multiscale. Everything that you can sort of think of is a multiscale problem effectively if you come really into an application and look into it in detail. And here's, for example, a few papers that we did, actually that we started pre-COVID on using this theory to show periodic outbreaks in epidemic systems, for example, and find early warning signs for epidemic transitions. And we used this theory of geometric singular perturbation theory to prove that, for example, if you have an epidemic system on a general network under waning immunity, so if your immunity, for example, to COVID is waning over time, that then you can have multiple big outbreaks that are coming quickly. Yeah? And I can tell you, well, on a personal note, I had COVID in Portland 5 weeks ago, and there's a new variant. It was unpleasant. So, yeah, so this waning immunity is kicking in, and most likely we will have a few big spikes in the future, I would say. Yeah? So that's the way it goes. You have to just sort of live with that, I suppose. Yeah, I mean, yeah, that's the way that sometimes is. Okay, so here's a little bit me showing that I studied in the US because that's the first commercial break. Because I've learned in America, you always need enough commercial breaks between every football game. So I thought, okay, let's adapt it to a talk. So here's the commercial break. I've written up more about this multiple timescale dynamics in this book. And I think if you're in Germany, it's freely available via Springer link now because of the deal. So you can just download it and have a look at it. And I cannot go through all the 800 pages here and cite all the colleagues that I would love to cite. It's just not possible. Yeah. So, but you can have a look in there. I try to be very careful with the referencing. Okay, I tried. It's about 4,000 references that I sorted. Hopefully this is sufficiently accurate, but you know, I still might have missed stuff. Yes, I mean, this might very still be possible. Yeah. Okay, So there's this general theory. Let me now come to a little bit more math, because that was a general introduction. So sorry if I was boring some people who know this already. So this is the statement of this Fenechel theorem. It's actually, in some sense, after you parse it, it's somehow just the generalization of what you have seen geometrically. So let's focus on interpreting this theorem here in this concrete example. So remember, this is this van der Pol oscillator thing, and there's this critical manifold C0, which is this cubic curve. And then we know already it's normally hyperbolic, for example, within this sort of magenta box or this purple box. So if you linearize at every point along here, you see that in this submanifold, which I get by intersecting this box with this actual cubic curve, then I have a submanifold that is compact and that's normally hyperbolic everywhere along. Yes? Because you can linearize and you see that everywhere the eigenvalues in these boxes are negative, actually. And then the theorem says that if you take that object, this submanifold that's compact, which is normally hyperbolic, you can perturb it, and what you obtain is a so-called slow manifold. So it's a slight perturbation of this manifold. So it's very close. It's order epsilon distance. It's actually diffeomorphic to the original piece. So it's really just a perturbed piece. And you see here that trajectory, this actual true trajectory, follows this singular trajectory as long as you are near this sort of black solid bit very closely. So you indeed see that this manifold must sit in a very small neighborhood of the true manifold, of the critical manifold. And you know that the flow is the same flow. So if it's directed, for example, upward in this example, also on the slow manifold, on the perturbed object, it will be actually directed upward. And the similar considerations hold for stable and unstable manifolds, meaning if stuff's coming in along certain directions, also these directions are sort of slightly perturbed. They still exist. So somehow the dynamics near this object, if you're normally hyperbolic, is fully preserved, just wiggled by epsilon effectively. That's the way you can view it. Okay, so this is the nice theorem that you have from Fenechel. And now comes the meta theorem if you don't have it. So if you don't have normal hyperbolicity, there's a technique called the blow-up, which is sort of, in some sense, much harder, which are these two fold points, for example, applies, where you can use a desingularization method to actually still make conclusions with linear analysis about a nonlinear problem, despite the fact that your linearization is degenerate, right? Remember, the definition was loss or normal hyperbolicity means all the spectrum is away from the imaginary axis. But if there's some spectrum on the imaginary axis, then this means somehow the linear dynamics of your linearized ODE is not very determined by your spectrum, because it's neutral. It doesn't get attracted, it doesn't get repelled. So you need to look at the nonlinear terms. But this so-called blow-up method allows you to actually look at linearizations despite the fact that you in principle should look at nonlinear terms. And the way it does it is in some sense the easiest case you can think of is polar coordinates. Okay, so how do I do this? So let's take this van der Pol thing as an example. We know that this point is not normally hyperbolic, because if you linearize in U, then we see that that point actually was a point where, in some sense, the slow scale and the fast scale mix, which are the points where you're expecting to be singular. What I've simply done here is I've taken the equation and I've also added the equation epsilon prime is equal to 0. I'm allowed to do that because epsilon is a parameter, right? I can just add that equation. Epsilon is fixed, is constant, so I can add this equation. But now, how do I analyze this? One thing I could do is I could take this point and try to do at this point, with this point as a center, a polar coordinate change, or a spherical coordinate change. I could say that point will be my origin of my spherical coordinates, and then I can just do a coordinate change, which is this map here, which basically lifts the original vector field that lives on the real space Rm plus n plus 1, because here it's basically 1 plus 1 plus 1. Because this is the epsilon encoding, this is the m and this is the n, and for van der Pol, m is 1, n is 1. So it's this. And then I can put in a polar coordinate change and then hope that after polar coordinate change, my system improves. Why can it improve? Because if you do a polar coordinate change, the point that you're having at the origin of your polar coordinates gets blown up to an entire sphere, right? Because polar coordinates at that origin are not invertible, because you have the entire angular dimensions that you carry around. So this means that I've inserted, instead of an equilibrium point, remember here, this point will be an equilibrium point because it vanishes here and vanishes here. But I've inserted basically an entire sphere at this point, but on this sphere, I have no dynamics. But then I can actually do a singular division. I can divide out with my radius, and then I hope that by dividing out, this 1 over r to the k, which is effectively like you are doing the same as inserting a P1 in algebraic geometry, then I can hope that the resulting vector field after all these coordinate changes and the singular coordinate change of dividing by 1 over r is better. And indeed it is. So this is the sort of meta theorem, which many people have worked upon. Here's a simpler version. So I take this point, I move it to the origin, and I also do Taylor expansion. And then this is a sort of normal form for a point where I'm not normally hyperbolic, a so-called normal form for a fold point. It's very easy. It's just a parabola. So when you see here at the origin, indeed, with epsilon equal to 0, you are 0, because 0, 0, 0 is an equilibrium point. And if you linearize at this equilibrium point, you get a 3 by 3 matrix. And you will see that this 3 by 3 matrix is also singular, right? You can do that in your head, right? You linearize that in u, v, and epsilon. You see that that is also a singular matrix. Yeah? So this means the linearization at this equilibrium doesn't tell you anything really, because you have a singular matrix with spectrum, only spectrum on the imaginary axis. And then you basically take this point in phase space. Here's this critical manifold again. I take this point in phase space and I blow that point up to a sphere. And then if I do that, and if I desingularize the flow on the sphere by dividing by 1 over the radius to a suitable power, then I induce a flow on this sphere. And if I induce a flow on this sphere, which is a sort of a desingularized flow, then I can hope that this induced flow is better than the flow I had before over here, which is extremely singular to leading order. And it turns out that that is true. Looks a little bit like a miracle, but I mean, in some sense, when people first prove desingularization theorems, they all look a little bit like a miracle, but that is indeed true. You can show that this is then non-singular in many cases, and the meta theorem as for all sorts of singularities where you lose normal hyperbolicity, this so-called blow-up method of inserting spheres will help you to analyze the vector field in a much better way than if you didn't do that. Right? And you have to play a little bit. There's a little bit of playing around because spherical coordinates are difficult because you don't want to calculate with them, except if you let your students calculate with them, because then it's a good exercise to keep them busy. Yeah. But in principle, you don't want to calculate with spherical coordinates. So one way to do it is to use charts, of course. Yeah. So you use charts on the sphere to take, you blow it up to the sphere, then you have a new space, but then you can, on that new manifold, use charts, and then you calculate everything in charts like you normally would in differential geometry, right? Okay, so that's a very cool theory because it allows you to treat these fold points geometrically in much detail. And lots of people have worked on this, and Dumortier, Roussari, Krupa, Smolyan, many people have worked on this, me included. I've also done some of these results in finite dimensions, and it's very powerful. So, okay. So now the problem is, this is sort of finishing the first probably part of my talk. Let me check how am I doing on time. Yeah, I guess I'm doing okay. I'm a little bit slow, I guess. When should I stop roughly? $25. So is it okay if I take sort of around 15 to 20 minutes, or is that okay? So then I will do that. I think that's adequate, and then you have your party on time. So very good. So now this is for the introduction of the theory that exists. Now, the problem was for many years, for many decades, people were wondering how to lift this theory from finite to infinite dimensions, right? Because it would be ideal if you could do just the same thing for a PD, right? That would be nice. So if you have a partial differential equation, you would think, well, if it looks, for example, like this should be one easy example. Easy in quotation marks is, of course, not easy, which is a reaction diffusion system that has a small parameter epsilon. And let's put it on the interval. Let's put it with Neumann boundary conditions. Let's make it one-dimensional in space. Let's make it as easy as possible. And then you would hope that maybe the same theory would apply. By the way, a second advertisement. There's a second book. If you want to know more about PDE dynamics, second commercial break, you can have a look at this book. Highly recommended. So, but today's goal would be, how can you do this sort of general theory for fast, slow PDEs? And that's hard. Yeah, and Navier-Stokes is implicitly one of these, and it's much too hard for us. So maybe start with reaction diffusion. Potentially, that's a bit easier. And many regimes, reaction diffusion systems surprisingly well describe actually Navier-Stokes. Yeah? It's quite surprising, but yeah, okay. So here's the references. So I will not talk about everything because of time constraints, but I thought I will put up the references. So what we have done is basically we have tried to follow this program from finite to infinite dimensions. We first tried to do the normally hyperbolic theory. We only needed tweaks for that because there exists already quite a bit of normally hyperbolic theory, and we found, we believe, the right tweaks. Then we tried to generalize the blow-up method by a technique that's basically motivated by numerical analysis. So we discretized the whole problem, and then we blew it up, and then we showed that this actually works. So, which is a sort of motivation that comes from computation, maybe very appropriate for the Zuse Institute in some sense. And then the last part, we did a sort of more purely analytical direct scaling, and we did it for amplitude and modulation equations, and showed that the generalization of the blow-up method is actually related to something called the renormalization group method in physics. And we have Alex Mielke here. You can ask him about amplitude and modulation equations. So for this sort of theory, it also seems to work well if you adapt it suitably, for non-hyperbolic points. So let me start a little bit. How would these slow manifolds in infinite dimensions look like? So let's suppose we have a linear problem in infinite dimensions. You can think of A and B as the Laplacian, if you like, and just think of L1 and L2 for simplicity as just scalars, if you wish. It could be operators and everything. And suppose you have a nice semi-group solution, like from your base functional analysis course, and you can solve this linear problem very nicely. Then you would anticipate, since there's a small epsilon in there, you should try to compare the semi-groups for epsilon positive with the semi-group for epsilon equal to 0. First, you define, as before, the critical manifold. So you just take everything that's in the first so-called formally fast variable, you set this equal to 0, and then you get the critical manifold. So this is basically, if A is the Laplacian, would be an elliptic problem. You solve that, and then, okay, that's the critical manifold just in a function space. So far, that's fine. You live in an infinite dimensional space, but there is a problem. One problem that you see, the best available theory that was out there was theory by Bates and collaborators. So that theory requires that these semigroups are actually close in a certain topology, namely in the C1 topology in time, mapping into a certain Banach space or into a certain Hilbert space. And if you do that, then you realize that if you look at this theory, you cannot allow that B here is, for example, the Laplacian. But you would want that because, in principle, many of these PDEs have differential operators everywhere, and you need to allow something like the Laplacian. So, and intuitively, for those who are not deep into this business, you could think of what's the problem here? Why in infinite dimensions do I have this problem? So I thought about what's the best intuitive explanation for people who are not in this business. And I think the best intuitive explanation is sort of this heuristic of, you might know that at least from an abstract level, you can view sometimes the Laplacian as an unbounded operator on certain function spaces. And it's unbounded, but you multiply it by something that is small. So in some sense, you have this generic problem of something really big times something really small, and you in some sense send both of these guys to 0, one to infinity and one to 0. And that is a problem because then you have to define what you mean by limits of this form. What happens if I send one parameter to 0, but the other guy goes to infinity? And that's actually not obvious. And that's the intuitive explanation why you need a new theory in some sense for PDEs. At least I think it's a good intuitive explanation. Formally, you can show that you need a new theory. You calculate, but from an intuition point of view, that would be the way to go. Okay, so what's the second problem? You think if I drop all the L's and I put all the Laplacians and I just even decouple the problem, it should be easy. So this is the easiest thing you can think of, sort of two decoupled heat equations on an interval with Neumann boundary conditions. And you can solve this explicitly with Fourier. You plug everything in, yes? And you think, okay, what's the problem? U should be fast and V should be slow, and that's basically it. But indeed, it's not true. Because if you think about it, if you look at the eigenvalues of the Laplacian, of course, they grow in magnitude, which means that even though you multiply it by a small number, eventually you will have the problem that epsilon times one of these eigenvalues could potentially be big again and could have the same size as the eigenvalues that come from the first part, from the fast equation. So there are modes, basically modes of the heat equation, on which you're evolving quickly despite the fact that you pre-multiplied by epsilon. That is difficult because then you somehow need to sort out all the modes. And this is a technique what is classically used as sort of a spectral gap. You somehow sort all the modes that are still sort of slow into one bin and all the modes that eventually become fast because the eigenvalues of the operator grow into another bin. And after you have sorted them into these two bins, you somehow have a new separation into fast modes and into slow modes. And in a linear problem, you can calculate this. But in a nonlinear problem, this is actually the hard part, because there everything is fed through the nonlinearity and you cannot disentangle the modes. That's the hard part. Yeah. Okay. So problem 3. Yeah. So lots of problems here. Problem 3, you want to localize everything for Finite shell theory. There's some really good theory for invariant manifolds in infinite dimensions that you could try to adapt, yeah, so-called inertial manifolds, but these are mostly global things where you haven't locally cut everything into pieces, into locally invariant pieces like we did in van der Pol, where we had little pieces where we could apply our Finite shell theory. And you want everything on finite timescales for this fast, slow, multiscale business. So this inertial manifold theory is good, but it needs to be a little bit of adaptation. So people have done this globally, and there are some nice books by Themann and Robinson and so on that explain this. And yeah, we need to adapt that theory too. There's even more problems. So there's lots of stuff that give you problems, including this pointer here. So there are, of course, very good invariant manifold results for special problems. For example, this is one that maybe people should know, which is the so-called Allen-Kahn equation, where it's not in a standard fast-slow structure, but it is a fast-slow problem. So there's a small parameter in front only of the Laplacian, and you see that this has a certain fast-slow dynamics. In the beginning, on a fast scale, you see for a very short time, you just start with an initial datum that converges to certain interfaces, and these interfaces then evolve on a slow scale, move towards each other and annihilate. Yes, this was analyzed by Karen Pego, for example, and many others, hundreds of people, yeah, who've analyzed this sort of Allen-Kahn type dynamics with small diffusion in full detail. And here there's a natural candidate for a slow manifold, namely it's just the manifold that's parametrized by the positions of the interfaces. If I take my interfaces and I parameterize the positions, then I have a slow dynamic on the space of positions, which is a finite dimensional slow manifold that's evolving. Very natural, right? And at some point, these positions collide, and then the manifold loses a couple of dimensions, and so on and so forth. And what Karen Pego have shown is that often it's very difficult to find that manifold exactly. What they showed is it's better sometimes to only get an approximation of that manifold. Yeah? So you don't want an exact geometric object, you only want an approximation. So roughly what you want is now in infinite dimensions, you want a merger of all these four sort of problems and theories. You want something that fixes the Spates problem of C1 in time. You want something that fixes the local to global inertial manifolds. You want something that fixes the splitting of the fast and slow modes that come from the interplay between the eigenvalues and the epsilon. And you want something that fixes this sort of approximation theorem. Yeah? So you want a theorem that basically says that there is an approximating manifold, and if you have extra condition like a spectral gap and so on, you have a true manifold. And we have developed such a theory. So this is joined with Felix Hummel in the beginning. So we have again this fast slow setting, but now A and B could be more general operators on more general Banach spaces. And the new tool that we brought in, I don't know if people are here in functional analysis use this a lot, are these interpolation, extrapolation scales. These are spaces that are sort of stacked into each other in the right way. So you can think of in the simplest way of, for example, fractional Sobolev spaces or spaces of derivatives with a certain fractional order. Then you know that, of course, the ones that have more derivatives are stacked inside the spaces that have less derivatives in a suitable sense. And the stacking of spaces actually allows us to do finer estimates than before. And we also actually localize everything by a cutoff procedure to make everything local and Lipschitz. So we develop certain cutoff techniques. And we also do a subsplitting of these slow modes to circumvent the problem that there's actually some modes that might evolve quickly despite the fact that they have an epsilon in front of them. Then we all sort of combine this with the spectral gap technology from inertial manifolds, fix some of the Bates technical stuff, and voila, in the end, after a long, hard work, you can actually find that there is an invariant manifold theorem. I will put it up there for the experts. For the non-experts, it's actually very easy to understand in the end. You take your sort of two-component system. You take in the slow component all the modes that are still fast because, say, the Laplacian has these big eigenvalues. Take all the fast guys, shove them into the first equation. Then you have the slow guys and the fast guys left. And then in the end, you indeed get a manifold where the slow guys are parametrizing the fast guys like in Finite. Yeah? So you get an invariant manifold like you would before, just it's now living in some Banach space. Yes? And we can prove that. So this is technically long, but in the end, sort of similar estimates come out. And we also have an approximation theorem that says, if you cannot do this geometrically, at least you have an approximating manifold under weaker conditions. Yeah? So we have sort of combined all these four problems and have, you know, a nice new theorem. Okay, the key trick, this is for the experts, you need sort of an adaptation of spatial versus temporal regularity. Maybe you have seen that before in math. You have a space that depends upon multiple coordinates, but somehow in one coordinate, you assume a certain regularity, say, for example, in time. But then if you are very regular in time, you might need maybe less regularity in space. But if you have more regularity in space, you might need less regularity in time. Right? And this trick we are exploiting here to prove these invariant manifold theorems. Yeah? So we are trading off a little bit of time regularity to make it less regular in time. And via these interpolation, extrapolation scales, we put in a little bit more space regularity, and that fixes all the problems, which I think is rather neat. Because it's an application of a general math principle. You somehow exchange regularities within spaces, which I think is a good principle to learn if you have never seen it. Okay, very good. So we can apply this to climate science, to the Stommel model. We have applied this. We applied this to neuroscience, to the Fitz-Nagumo equation. We also showed that some of the stuff that people have shown before for particular systems, for example, there was a nice slow manifold proof by Kuehn, Menno, and George Haller for the Maxwell-Bloch equations, that these Maxwell-Bloch equations, even though they are pretty ugly, they are not reaction diffusion or anything, they're much worse than that actually. There is a slow manifold, and this theorem of Haller and Menno that pops out as a special case out of our theory. Some of the Fitz-Nagumo invariant manifold theorems pop out as special cases out of our theory, which is nice. So this means this theory might be sufficiently general and a nice step forward for invariant manifolds in infinite dimensions. Okay, very good. So we can also do this for fast reaction systems, meaning we can move this epsilon here and put an extra epsilon in front of here. This is joint result with my postdoc Jan-Erik Sulzbach. So you can put the epsilons in different places, and we can still show the existence of manifolds. And this theory of fast reaction systems was being very prominent in many cases. So there's a long list of, Daniel Hillhouse started working on this in the 90s, and there's hundreds of papers on this, and we can apply our theory to this. Very good. So now, how much time do I have left for the last part? Let's see. 5 minutes. Okay, I will do 5 minutes. I will just tell you basically that there's also a way to fix this blow-up method in infinite dimensions, and we have developed two variants of it. And I will just give you the gist of the two variants, how to do the blow-up in infinite dimensions. First variant, take one of these singular points. Yeah. You know that this origin is singular, because if you look at this very precisely and you linearize, you see that you have loss of normal hyperbolicity at the origin. You put a Laplacian on top of here. You try to do the same thing that you did before by doing a geometric blow-up analysis, putting at the singularity a blown-up sphere. And indeed, this can be done. Yeah. What you can do is start with this problem. Why start with this? I will skip it. There's a good motivation from functional analysis and Grant-Rabinowitz theory to start with such a problem. Why not the fold? We can also do the fold, but we started from this, which is these two crossing lines, because it's functional analytically maybe a bit easier. Yeah, and then you can show, if I can get the thing to flip. Okay, maybe I should do it like this. So we can show, this is joint work with Maxi Engel, that indeed there is a blow up. And the trick we do this is we take this PDE, we discretize it in a Galerkin sense, so spectral Galerkin. Yeah. So after you do spectral Galerkin, we chop off at a certain value, meaning you basically do a numerical analysis technique by taking the system, discretizing it, chopping off at a certain value, and then you blow up all these finite dimensional ODE systems for arbitrary size. So for every chopping off point for this numerical discretization, you do a blow up and you show that all these blow ups work, and you can track trajectories up to an arbitrary Galerkin truncation level. Not yet up to infinity, but to an arbitrary K0. And then we show, for example, quite interestingly, that in our first blow-up attempt method, you get actually something that's called a free boundary value problem in the blown-up charts on certain big spheres. Sort of rather cute. And you can show that the results from finite dimensions, namely the dynamics that are in this picture. So the picture is you get attracted to here, you flow slowly, you either change here, or you get attracted to here, you flow slowly, or you jump over here. That this picture is also true in infinite dimensions for certain solutions that are near the homogeneous solutions, which is sort of nice. Yeah, so Very good. And we can also do this for the fold point, which is the generalization of this parabola. People should know this now. Here's the u squared minus v that you know from the van der Pol. Now it's just in space-time. And indeed, we can do the same thing in space-time, do Galerkin, do it the right way, do the desingularization, and show that there's a dynamic passage through a fold point in infinite dimensions for a PDE that you can analyze via spheres that grow in dimension. Yeah? Okay, so to conclude, let me say all this Galerkin view and the slow manifold view that I've said, they are consistent, meaning if you do the Galerkin truncation and you look at the slow manifolds that we got abstractly in the first part, they match. We have a theorem that says, indeed, if you do the abstract view and the numerical analysis view, you can match these manifolds and they are close to each other. That's what it's saying. Yeah? So all of this is incredibly consistent. Very good. And yeah, let me maybe finish with this, although I won't finish this. I will just say a few words. This is for Alex, so who has worked a lot on modulation and amplitude equations. I thought I would put it in. We can now also do this for amplitude equations on unbounded domains. So if you have something like Swift-Hohenberg and you have a slowly drifting parameter, we can blow it up and we can show that on the spheres in the right charts after the blow up, we get a non-autonomous real Ginzburg-Landau equation, which is what you would expect. And we can prove rigorously that this non-autonomous real Ginzburg-Landau equation is a good approximation to the original problem. So we basically can use our blow up to extend sort of the passage for modulation or amplitude equations. So let me skip that and let me go to the conclusions. So I just wanted to say we are really extending this. So you can do this in infinite dimensions. Yeah, this is the theorem. You can actually prove that. And I want to wrap up in 2 minutes or 1 minute. 1 minute, I think, is fine if I do a 1 minute wrap up. So what I've shown you is there's this finite dimensional nice theory, which I spent far too long upon because I was so slow. So apologies for that. I'm still suffering a bit from a COVID infection a few weeks ago. It's a little bit, the muscles are not as quick as they used to be. But what I've shown you hopefully is that, you know, there's finite dimensional singularities and there's this nice toolbox of having Van shell theory, manifolds, patching stuff together, blow up, and so on, that analyzes all these sort of trajectories of multiscale systems, like the sort of relaxation, oscillation, and Van der Pol. But we have now started to lift this slowly. Yeah, it's a little bit of progress. It's a huge thing in a sense. It's a little bit of progress to lift it to certain classes of evolution equations in infinite dimensions and show that some of the techniques also work if you are careful in an infinite dimensional setting, which brings us a little bit closer to this dream of Prandtl, I guess, to do multiscale analysis in infinite dimensions. Yeah, and there's lots of work. There's other singularities we work on, other blow-up variants, more relations to fluids, and all of this is in progress. And if you want to join in, there's lots of cool open problems now that we opened up this area of infinite dimensional geometric multiscale analysis. And there's stuff on my webpage that tries to be easy to remember by its name. And then thank you very much for your attention.
Yes, thank you. Okay, the floor is open for questions.
People are hungry.
Yeah.
Thank you very much for this very nice introduction to the network of today. I really learned a lot. But at the very last step, I missed something. So how does it really work? So going beyond point is here.
Yeah, so the idea is that if you have the vector field, you can lift it from your original system via coordinate transformation to a vector field on the sphere, right? Because you're only changing coordinates. Huh? But if you then calculate that vector field on the sphere, then, or maybe I should draw this. Do we have chalk or something? Yeah, maybe I'll draw this. Yeah, but I mean, you just are persistent and you do it. I mean, that's fine. I mean, you just sit and calculate. I mean, so let me give you a simple example, okay? Let me give you a simple example. Let me draw it maybe like this. So let's put here an equilibrium point, and let's suppose the flow looks something like this. This is the example I like to use. Maybe something like that. This is a single scale system, but should be fine as an explanation. This is the wrong way. I think this should go this way. This should go this way. This should then go this way. So let's suppose this is the flow. And here you see, if you would insert now, this flow is completely singular on a linear level because there's sort of directions on a linear level that don't have a separation into stable or unstable. But now if I do this, and I put in here a sphere, then on that sphere, I will get new equilibrium points. Say here, 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 and here. Now, these are 6 new equilibria that I have induced by this singular coordinate change. And I can show if I take linearizations at each of these 6 equilibria are then partially hyperbolic, meaning there is spectrum that is actually away from the imaginary axis. So this means that, roughly speaking, by inserting a sphere, I have gained the ability to linearize. So it's basically saying I trade off, I put in a geometric object, and after I put it in, I'm allowed to do linear analysis. If I don't put the object in, I'm not allowed to do linear analysis. Does that explain it a bit better? Okay.
More questions? Yes, back in the room, and then Alex.
In that classical case, like this is done again at the beginning, it is one epsilon, we have 2 different epsilons that are allowed to be both 0. In this case, when we go to limit cases, we would have like 4 limit cases, right?
Yes, I mean, if you had multiple small parameters, there's theory for that. Roughly speaking, what's happening then is, suppose you had one small parameter, say epsilon, and then, I don't know, another one, say epsilon tilde. Then, of course, there's this sort of thing when epsilon tilde is 0, you send epsilon to 0. But then if you send both of them to 0, you basically have to find a subdivision of parameter space that tells you maybe within certain regions there's a certain behavior. So if you have an asymptotic dependence of this guy on the first guy, then you need to know, okay, how do I go to 0 in these regions? And depending on the rates they are relative to each other, you get a different theory potentially. Yes, so there's theory for that, there's a Fenechel theorem for that, and there's also blow-up analysis in multiple small parameters. So that works. It's just the calculations are not double, but more like triple in size.
Yeah. Alex first, and then back in the room.
Question concerning the spectral gap problem. If you have this base problem, that I say, so if you do a spectral gap, you take the slow variable, you take the square root epsilon number or 1 of the square root epsilon number of the slow variables, or how do you?
So yes, I mean, what I need to do is first I need to look at the slow variable and I split off some of these. And the way I split them off is I introduce a new parameter that's related to my original epsilon. They have to be in a certain relation, and this cutoff parameter has to go to 0 slower than the epsilon. So this means there is a cutoff that's controlled by the epsilon itself. And with this dynamic cutoff, I can sort all these variables into the right order. And then I take all those formally slow guys that I cannot treat, move them into the fast guys, and then I get my reduced manifold. So,
typically, you need the spectral gap to be wide enough to get
yes, that is true. We need it wide enough. And there's a condition that says if you have the spectral gap condition that's compared to the condition of all the other stuff, the nonlinearity and the epsilon and everything, if you have the correct inequality, then you get a smooth manifold. And if you don't have that, then we don't get a manifold, but we get an approximation theorem in the sense of Kuehn-Pego. So we get a theorem that says we are not having a manifold, but we have enclosedness of solutions in this normally hyperbolic regime. A little bit like what Kuehn-Pego proved. They proved approximating invariant manifolds. They are not smooth, nice objects, but the solutions flow in the right path.
What kind of variance do you have in mind?
So, I mean, the variants, of course, currently are for a very particularly sort of structured singularity, meaning that there is in the fast equation a bifurcation point with a certain spectrum, and we want to blow that up. But of course, in the end, you would like blow up stuff that also works on much more complicated invariant sets. And we have started this to do it on periodic orbits, and maybe you want it even on a chaotic set, who knows? So you have some more complicated invariant object that you're trying to blow up, and then you need a variant of this blow up because this pointwise blow up just won't work anymore, just putting in a single sphere. And also this sort of stuff, how to say, won't work for equations that are not in this immediate structured form where you can see where the singularity is sitting. Think of Navier-Stokes, you don't know where the singularities are. Probably they're infinitely many at infinitely many scales, and you still want to blow them up. But how do you do this? You need a variant of the blow up that somehow works in a non-standard setting with more than one singularity that stretches across all scales. That would be the dream, you know, if I solve this when I'm, you know, getting carried out in a wooden box out of my office when I'm 90 or so, then I'm happy, you know. But it's a hard problem. So, so you need to start somewhere. And what I mean by this number 2 point is we need to start with simple variants to understand how they work. And then we can progress to more complex variants for the blow-up. It's a little bit in algebraic geometry. You started this in algebraic geometry with a planar curve, right? Blow that up. And then people developed, okay, this can be done in arbitrary dimensions.
Okay, I think there is no storm of more questions now. I will retain my questions to talk to you about in the sun. And let's thank Christian for the very energetic talk. And actually also for coming. He is under a lot of time pressure towards the end of the semester, and he came here this morning. He's going to go back in the late evening, and so thanks very much to take that on you.
Yeah, maybe I repeat that from my side, and maybe in the name of the students, I think it was perfect that you spent so much time on the stuff that is so easy for you in all review. So that was very good. Thank you. Right? And now I ask you for a little patience, and I ask Michael Hintermüller, Lucy Helfmann,